Okay, class. So this is the last part of the topic of leaching and having to determine the number of stages analytically, not having to rely on equilibrium diagrams or not having to rely on graphical techniques in determining the needed number of stages for the degree of recovery that is stated in the problem for our solute in the case of the process of leaching. Okay, so now we will be looking into a sample problem on how to determine this number of stages. Now, before we do that, there are actually two types of processes wherein we can determine the number of stages, or in the case of washing for a batch process, uh, it is the number of batch processes. When we speak of batch processes, we put our solid in our leaching equipment, wash it with the liquid, and then drain. And then again, put it back, wash it with the liquid, and then drain. So how many washings in terms of the batch processes are we looking into? So this is for a batch process. So in here, we're not accounting for N, which is the number of stages, but rather our N would be the number of washings. So we just place our solid in the leaching equipment as mentioned, then wash it with the pre-measured amount of pure solvent. So how many washings? So for one washing, drain, then another washing, then drain, until such time that you have almost like depleted the solute present in your solid. So we have a very straightforward formula in determining the number of washings. So the number of washings is associated with the number or the amount of the solute remaining in the solid or the insoluble solid after that particular number of washings. So how much solute remains in the solid is equated to 1 over R prime quantity R prime plus 1 raised to N. This R prime here is defined or is the representation for the amount of solvent decanted divided by the amount of solvent remaining with the insoluble material. When we decant our washings, that way we can do subsequent washings to our solid that is being processed in leaching. We don't 100% remove the wash solvent. There are still wash solvents that remain in our solid. So this particular amount of solvent remaining is our denominator here for our R prime. So the amount that was decanted is subtracted to the original amount, because as I have mentioned, it's pre-measured, then that's the amount remaining on your insoluble material. And that particular, and the quotient of these two is your R prime, and it's being placed here. So you can straightforwardly determine, or right away you can determine the number of washings based on the stipulated amount or acceptable amount as per design of solute that should remain in the solid. So meaning if you have an objective that only this much of solute should remain in your solid, so that would be the value that you're going to place here. And that value will be equated to this expression. And right away, you can determine the number of washings. Now, that's for a batch process or for batch processes. Now, for multi-stage processes, it's a different thing because this time we're not accounting for the number of washings, but rather to the number of thickeners in which your solid is to be processed. That way, we have also, as per objective, the remaining amount of solute that remains, the acceptable remaining amount of solute that remains in your solid in your last washing. So if this is your last thickener, so this is your remaining solute from your solid or in your solid after it being processed in thickener N in this case. Okay, so this is your solute. So the S that you see here represents the solute in your uh, solid, remaining in your solid. And the W that you see here represents the solution. So when we speak of the solution, it's the solute with the solvent. Okay? So S is only solute, but W is the S plus the solvent, which is most of the time water. We use these two representation S and W for the underflow. So these are all underflows. This one, these three. What about the overflow? So your overflow will have a different representation. You have to be very careful because this is how Colson represents the different parameters for leaching. For the solid content of your overflow liquid, he represented it as L. Actually, these are arbitrary representation. You can have your own representation, any letter that you like, but it's represented here as L. I'm referring to the solute present in the overflow. As to the total amount of solution in the overflow, meaning it contains the L, the solute, and the solvent, that would be the small w. So it's not big W like here in the underflow, but it's small w. The solution that remains or the solution that is present in your overflow. We don't say that remains in the overflow because the solution remains only in the underflow. It's not supposed to be there because when we speak of solution, it has some solute present on it. So the small w is your solution in the overflow. The L is your solute in the overflow. If you're so used to representing a particular stage in all the separation processes that we have discussed by N, small letter N, we represented it as small letter N. Colson represent a particular H or nth stage as H stage. So this is the eighth stage or the eighth thickener. It's difficult to pronounce. The eighth thickener. Now, equivalent to the nth thickener. Whereas if we refer to McCabe and John Copley's, the last of the thickeners or the last of your equipment should be represented by capital letter N. Colson represents it as small letter n. So the last is subscript N. A particular stage is H. So sometimes it's so easy to, when you look at your solution, it's so easy to get confused whether what you have written is really H because it looks similar to N. But nonetheless, when you do your material balance, the way they are written is totally different because in here, you're only balancing until this part or you're only balancing this part or this part. Depends on which part you'd like to balance, but you ended here. But in here, this is really the end of your processing because this is your last thickener. Okay, so this is how we represent things in Colson. Now, one thing more, now you don't have the x, small x prime. Notice, in the previous problem we have discussed, which is also from Colson, the representation of the concentration is small x prime, which is solute over solvent. Now this time, he went to the actual representation or he used the actual representation of the concentration of the solution in leaching. Whether the solution that we're referring to is in the overflow or underflow, we're still referring to the same solution because they are said to be equal in concentration. So now it's represented as capital letter X. Why is that? Because we represented, this is now rather to be understood to be solute over solute plus solvent, not just solute over solvent, but this X is solute over solute plus solvent. So these representations have to be clear. That way, when we process our last sample problem for leaching, it's clear as to what these particular representations or letters represent. Okay, now we move on. There are things that we need to define in terms of the parameters or the variables that are present in the formula that we will be using that will determine the number of thickeners for a multi-stage leaching process. Whenever you see the R, that R could represent all these three ratio. It could be the amount of solvent discharged in the overflow, over the amount of solvent discharged in the underflow, or simply amount of solvent in the overflow over amount of solvent in the underflow. If this is not possible, since you do not know the solvent present in the overflow and the underflow, you can replace it with the solute. If this solute is not present, you can represent it with a solution. Now, these three equivalent representations of R will hold true if these assumptions are true for our leaching process. So solution concentration in the overflow and in the underflow are the same, of course, because this is the primary principle that we are adhering to when we speak of leaching. If this assumption is true, then all of this can be your representation or could be used as a manner of determining the R. We are to assume that there is perfect mixing in all our thickeners. The solute does not get adsorbed in the solid. The amount of solvent removed with the insoluble solid in the underflow is constant and independent of the concentration of the solution in the thickener. So take note, the amount of the solid in the underflow is constant. S, that's insoluble solid is not S rather, but B in our representation. The insoluble solid in the underflow is constant and is independent of the concentration of the solution. Whenever that case, if this is true, then this would also be holding true. The amount of solvent leaving each thickener in the underflow will then be the same. So if the solid is fixed, then the amount of solvent present together with your solid in the underflow for each of your thickeners should be the same or equal. And then the amount of the solvent in the overflow are equal. If the solvent leaving in the underflow is equal as a consequence of the insoluble solid also being constant in your underflow, this one follows. The solvent present in the overflow will also be equal. All these assumptions have to be met. That way, this would also hold true. Now, in our next calculations, we will be using all these representations. Let me see. So your small w is the quantity of solution in the overflow, which you have seen already in the illustration and pointed out to you. The L is the amount of solute, which was also mentioned. The S is the amount of solute in the underflow. So you will have a corresponding subscript here depending on that particular or where that particular stream of your solute came from. Okay, so this could be S sub 1, S sub 2, it depends. But if it's 0, that's the amount of solute originally present in the feed that was processed in your first thickener and so on. W is the amount, so this is capital amount of solution in the underflow. W sub O is the amount of solution in the feed. So the subscript O here for capital letters S and W represents or denotes that it's the amounts for the feed. N is the minimum number of washing thickeners, so or the number of thickeners, and X, the capital letter X, is mass of solute over mass of solution. So a while ago, I have mentioned all this already in our illustration. So this is just a summary of everything, of all the representations that you will be encountering in our sample problem later on. Okay? Now, we have this formula for determining the number of washing thickeners, which is dependent on the R. The R is any of the three that was presented to you in the previous slide. But most of the time, that R is this. But if there's a time that this one cannot be determined or it's impossible to determine, but you can have any of these two as a replacement. Okay, so you have here the R and the F. The F here is also dependent on the R, as you can see. So this F that you see here is your R minus 1 over R raised to N plus 1 minus 1. If you're using a pure liquid solvent, and this is often the case, this F is equal to the solute present in thickener N divided by the solute present in the feed. Okay? If you're using a pure liquid solvent, the F is equal to the ratio of the solute present in thickener N divided by the solute present in the feed. This one is solute present in the underflow of thickener N, because we know that S is for the underflow together with the capital W. And again, the right side would still be the same. Now, another alternative or another formula to determine the number of washing thickeners would be this one. This time, together with the R, so you have the R here, you're now using the capital letter W, the solutions in the feed and in the last thickener, underflow, the underflow, solution in thickener N, and this one is the solution, or this is actually your solvent. Your solvent that is being fed on the last thickener. This is your pure solvent. So if you find that you cannot solve using this formula, the N, you can solve the N using this formula. Okay? Most of the time, this particular set of formula will work for a constant underflow leaching problem. If we have a variable underflow leaching problem, it's suggested, and actually it's impossible to solve for the N using this formula because we don't have this. You really have to do, in our language, you have to do it mano-mano, or you do it stepwise until you reach the acceptable concentration equivalent to the concentration that you have pre-calculated before you have started solving for the concentration of the shall I say, the nth thickener, or that's the last thickener. But how you go about determining the concentration of the nth thickener will start with the concentration of the first, the second, the third, until you reach a particular concentration that is comparable to the one that you have pre-solved or pre-calculated. You will know as we will process a particular sample problem later on. Okay? So how do we process a problem in which there is variable underflow? So washings for variable underflow. You have to do a balance on the whole system based on the solute and the solution. So you just simply account for the total solute coming in to your system. So you have two streams to account for that. The SO for your feed and the L sub n plus 1 for your solvent. Most of the time, this is 0 if your solvent is pure, because we're making an overall balance in terms of the solute. We equate that to the solute that leaves your nth thickener, specifically the underflow of your nth thickener, and the solute that is leaving your first thickener. Okay, the overflow this time, because L is for the overflow. Now, from this equation, we can get this expression. This one is just taken from this. This is the solute present in the overflow of the first thickener. And actually, this tells you already of the recovery. How much of the solute present in the original solid in the feed were you able to recover? This one. If you wish to make a balance on the whole system based on the solution, then it should be based on the solution. So this is for your solvent, and this is for the solution in the feed. We equate the sum of these two for the solution in the overflow of the first thickener, and this is the solution of the underflow of your nth thickener. From here, we can get the W sub 1, the small W sub 1, which is the solution. Yes, the solution present in the overflow of your first thickener. So this one was just taken from in here. What's the purpose of having this two? The purpose is for you to be able to get a formula for expressing the concentration of the solution inside the thickener and in the underflow. Actually, it's the same concentration of solution that is also in your overflow, because concentration of the solution in the overflow has to be equal to the concentration of the solution in the underflow. So what was done here actually is your L1 was divided by small w sub 1. So we copy that and we copy this and we have this. You can do this for the whole system. This is for the entire system. But if you make a balance on the first H thickeners, or we shall say this one in the usual SEPA thing representation on the first N thickeners, small n that is, because the last is capital N, the same holds true with this one. You just account for the solute, for the first H thickener, entering and leaving, and then the solution, and then these two. This as the divisor and this as the numerator. That would give you, we will be using this formula later, same thing with this. This will give you the concentration specifically of the underflow solution and the concentration of the overflow solution. For your thickener H plus 1. In that case, that would be the thickener after thickener H, because when you speak of H plus 1, then that must be referring to the next thickener after thickener H. So this is the manner of determining concentration. So both of this have solute as the numerator and solution as the denominator. So actually, we do material balance just like the way we do it. We account for the total streams coming in and the total streams coming out, or we account for the total amount of this particular coming into your system and the total amount that is leaving, and we equate the two. Okay, we will use this principle. There's no need for you actually to memorize. If you understand this, there's no need for you to memorize, as long as you understand how, you know how to do about balancing for the entire system of thickeners, or balancing only for the first H thickeners of your system of thickeners. Okay, so this is our problem. This is our last problem. And what is good about this problem, I like Colson a lot, because his problem makes you think, although he gives you already the answer, but the solution to the answer is actually not specifically written piece by piece. So you will just be provided with the number, but you will have to think still where the number came from, though you have already the solution. So your solution is just the guide, or the final numeric value for the answer that he is requiring is there, but you will still think on how he was able to get the values that he used. Okay, so this fourth sample problem will be determining the number of washings. The number of washings for a scenario wherein we have a constant underflow, and for a scenario wherein we have a variable underflow, all using the same set of data referring to the same problem. But for the variable underflow, of course, you are to be provided with the relationship between the concentration of the solution and the amount of solution removed. Because in this case, the amount of solution removed is a function of the concentration of your solution. Okay? In here, a plant produces 8,640 tons per day, equivalent to 100 kilograms per second of titanium dioxide pigment, which must be 99.9% pure when dried. So just like the third sample problem, the solid after being washed in the thickeners will be dried. After drying, it is the goal that your titanium dioxide pigment would be 99.9% pure. Meaning if there should be any solute remaining on it, that would only be like 0.1%. Because when we speak of drying here, it's understood that all the water has been removed already. Now, the pigment is produced by precipitation So the titanium dioxide, it's referring to the titanium dioxide, was produced by precipitation, and the material as prepared is contaminated with 1 kilogram of salt solution containing 0.55 kilogram of salt per kilogram of pigment. Now, this is the understanding of this statement is very important in the process of determining the required information, or in the subsequent processing of the information provided. So it's very important that you understand that when this titanium dioxide pigment was processed, it is contaminated with 1 kilogram of solution. The 1 kilogram of solution contains salt and water, and the amount of salt present in the water is dependent on the amount of pigment that is precipitated. So if you have 100 kilograms of pigment precipitated, then the amount of salt present as a contaminant is 55 kilograms. But this solution that is being referred to in here is to be understood, it's a solution of salt and water. Okay, it's just salt and water, and the amount of salt present in this solution is dependent on the pigment that is being produced. Okay? The material is washed countercurrently with water in a number of thickeners arranged in series. How many thickeners will be required if water is added at a rate of 17,400 tons per day, equivalent to 200 kilograms per second? And the solid discharge from each thickener removes 0.5 kilogram of solvent per kilogram of pigment. Now, it's explicit here that when you are asked to determine the number of thickeners, the solid discharge from each thickener removes only this much of solvent per this much of pigment process. This is fixed for all your underflows in your thickeners. So since this is fixed, the first scenario here is a constant underflow problem. A constant underflow problem requiring for the number of thickeners. Because of this, from each thickener, so from each thickener, this is already fixed, the removal of the solvent based on the amount of pigment processed by a particular thickener. Now, the next scenario is what will be the required number of thickeners if the amount of solution removed, this time, the amount of solution removed in association with the pigment varies with the concentration of the solution in the thickener as follows. So this is a case of variable underflow. So if you have noticed, if you will read Coulson, if you have a copy of this Coulson, this particular set of data goes with this particular question. So meaning this time you don't have this relationship fixed for all your underflows. But this time, the relationship between amount of solution removed is dependent on the concentration of the solution present in the underflow. And you have this relationship. Now, the concentrated wash liquor is mixed with the material fed to the first thickener, just like the way it was presented in our illustration. The wash liquor, the concentrated wash liquor is referring to the overflow from the last thickener being mixed with the material to be processed prior for the mixture of these two being fed to the first thickener. So meaning your feed to the first thickener consists of your overflow from that same thickener mixed with the feed from a particular from the process. So whatever is your feed from a process that produces a particular solid, it's being mixed with the concentrated solution coming from the first thickener. The mixture of the two is now the feed, the entire feed that will be processed by your first thickener. So we have two scenarios here, and it's very important that we will understand how we go about finding N for the two scenarios. The first one is easy because it's constant. We have something constant. But the second one is quite challenging. Okay? But of course, we can do material balance step by step in that case. That way we will be guided as to the correct way of finding the unknown. So I'll pause the recording for now. Give me just a breather, then we'll go to the problem. Okay, so we will continue now, class. We will continue with the illustration, which has all the information that was given in the problem. Okay, so we'll start with the given, of course. So in terms of the given, we don't know our thickener, so we will have here there was a mention in the problem that we will dry our titanium oxide, and it's a requirement that it would be 99.9% pure titanium oxide. So in here, we have the feed. And this is 100 kilograms. I'd like to use na lang the values that are in kilograms, not the tons. Titanium oxide. And ang contamination, so with 1 kilogram solution. This solution is the contaminant or the contamination. Now, this solution is 0.55 kilograms salt. This 1 kilogram per second of contamination present in your titanium oxide as it was prepared has this 0.55 kilograms of salt per kilogram of pigment. And this solution, the solution, is composed of salt and water. So this denominator here for per kilogram of pigment will allow you to determine the actual contamination present, that's the solute, in the form of the salt when you have this much of solid that was produced by precipitation. So we have here our, okay. Let me just pause class.